Hello and welcome to the Worldwide Center of Mathematics Advanced Knowledge Problem of the Week. This week we have a kind of physicsy problem concerning a particle moving along a circle. However, the velocity is non-constant, and we want to show that in any dimension, the radial part of the radial component of the acceleration is pointing directly inwards, and we want to find the magnitude of the radial component of our acceleration. So let's start out by finding something. So we only know p of t. Velocity is not constant. Velocity is not constant, so we want to, of course, relate position to its derivative, which is going to be velocity. And another thing to take note is that p of t is a vector, however, r is a scalar, so we want to find something we can differentiate that is not a vector, so it'll be more useful to us. So we're going to take the dot product of p of t with itself. Of course, that's going to be equal to the radius squared, and that's of course because they're the same vector, so they're obviously parallel to each other. So that's also equal to p of t squared, which will come in and be useful later. So let's take a derivative on this. Of course, we're going to use the product rule on this side, and r squared is just a constant. So taking a derivative, we have using the product rule, we have p of t dot v of t, which is position's instantaneous rate of change at a point, and then the same thing, except we have this other one. Of course, they're commutative, so we can have 2 p of t dotted with v of t is equal to 0, and the 2 is going to go away. And so what this tells us is that p of t and v of t are perpendicular to each other. So I'll just draw that up there for future reference. And but we haven't gotten to acceleration yet, so we're going to take another derivative here. So for the first term, we just leave this alone, differentiate that, so that's acceleration. Second term, differentiate this, leave that alone, that's v dot v, which is the magnitude of v, or the speed squared. And so now we're going to look at this acceleration, see if we can simplify it or find something useful about it by breaking it up into its components. So we've broken up acceleration into its radial component and its tangential component. And the radial component, of course, is going to be parallel with our position vector. So it's going to be some scalar multiple of t, scalar multiple times position. Of course, that could change since velocity is not constant. And the tangential is going to be another scalar multiple times v, at least in 2 dimensions, which is what we're looking at now. So yeah, we're just going to plug this in. So what I've done here is just plugged in our component-wise acceleration into this more general acceleration. And this dot product is going to distribute, and of course P of t dot V of t is 0, so we don't have to worry about this, which is good because we can't generalize the tangential acceleration into higher dimensional spheres or hyperspheres, I guess. So we just have we just are left with this radial component, and this, of course, is equal to r squared. So the radial component of our acceleration is this scalar multiple of our position vector, which we can see it's a negative number because r squared is going to be positive, and so is the magnitude of the velocity or the speed. Of course, that's squared as well. So we have some negative scalar multiple of the position. So looking back at our circle, acceleration's pointing directly inward. The radial component of it is, at least. And then taking the magnitude, we just have the magnitude of each part. This is just a scalar, this is a vector, so we're taking the magnitude of our vector, and that's equal to r. So one of them will cancel out, and this is our the magnitude of our radial component. So thank you for watching. I hope you enjoyed this video. If you did, stick around for more problems of the week or to subscribe to our YouTube channel. You can also check out our website if you're interested in math, which you probably are. So yeah, thanks for watching and have a good day.